Okay, this video is about the memory management, main memory management of the operating systems, and actually we are using the operating system concepts book written by Silberschatz. So if you somehow found this video on the YouTube and if you want to go for the textbook, you can go with the operating systems concept textbook. But in this video, I will basically talk about paging, segmentation, and some algorithms related to them. And I'm going to leave the numerical example to the next video. So following to this video, I will also shoot another numerical example video there. I will solve some questions, and then I will simulate how the paging or segmentation is working on the operating systems and what are the difficulties. Okay, so today we will talk about the swapping. What is swapping? How do you make some moving some processes to and from the memory? Memory allocations, segmentation, paging, and some samples from the real world and what are their usages in the real world. Okay, so let's start with the base and limit registers. First of all, as you can remember, the processes are running in their own address spaces. Okay, so this is one of the biggest differences between threads and the processes actually. So each process is running in their own address space. So for example, if you allocate a process, if you allocate some memory to a process, let's say this address space is allocated for this process, then this process is running in this space and cannot access somewhere outside of this allocated space. If it tries to access, then this is a security vulnerability. Actually, if you try to access to the memory space of another process, let's say, then this process can also attack this process, change some content of this process, or even can read some crucial information like the passwords or the usernames, which is already used by this process, some variable, content of some variables. So this is a security risk for the operating systems. So most of the time, operating systems are protecting processes from each other, and they are operating systems are allocating some memory for the process only. And here the protection is done by base and limit registers. So if a process tries to access some address space less than the base value, which is the starting value of this process, memory allocation area, allocated memory area for this process, then this is something memory fault. Okay, later on we will give some names special to page fault or something like this, but you can, for now, you can assume it's a memory fault. Or if a process is trying to access somewhere beyond the limit value, then it's also a memory fault. So a process is limited with the base and the limit value. So actually we will call this as the size of the process. So for example, if the process here is in the mid is the case, then we have a base value which the process cannot go below, or this is the limit value. So base plus limit will be the maximum value this process can access. Actually later on we will talk about the logical and the physical addresses. So the process is considering itself as the only process running on the memory, so there is no other processes. That's what the process is assuming. So for example, this process has a logical address which is starting from 0 and going up to this value. So a process cannot access any value greater than this limit value. Okay, so we place a process in here, and this is the base value where the process is starting, and it's limited with these given values. So this is the basic check before accessing to the memory. When you have an address request from the process which is running on the CPU at the time, we check for the base and base plus limit, which is the maximum value this process can access. And then if all the checks are okay, I mean if both of these checks are okay, then you can access this memory region, this memory unit, and then you can read any value over there, or you can write something over there. But if there is a failure of any of these checks, then it will be a trap, or it will be an address error, or it will be a memory fault, or whatever you call it. Okay, so let's go with some timings. We have, okay, actually this is how a program runs, a process runs. Okay, so you start with a program, a source code. And this source code, let's assume it's a C programming language, or you can use any other programming languages like C++. Actually in Java or in .NET, the things are a little bit different because, you know, there is a virtual machine running in here or a framework running in here, so you are producing some bytecodes. But let's assume C for this case. Okay, so you have a C source code in here, and then you compile this source code, and then you have an object module, okay? After you compile this code, it's an object module. It's not running, in fact. It's still stored in the disk, in the file system, and then, but what we have is a machine code, okay? A machine executable code. Actually, if you run a Java code in here as a source code, if you compile it, and at the end you will have some byte codes, which is also executable by the Java virtual machine, not the operating system, but the Java virtual machine. So you cannot run a Java program directly without a Java virtual machine in the operating system. Anyways, after this creation of the object module, the source codes, you also need some linkage, okay? Because let's assume you are using some libraries. Let's assume in C, for example, you have included some files like standard input-output header file, stdio.h, and then you need to link these files and generate a loadable module, an executable module, okay? Until this point, you have the source code compiled and some already compiled libraries. And at the linkage step, you link these libraries and the object module, and then you can load this program into the memory. And when you load this program into the memory, now you are executing a process. Okay. Until this point, before the loading step, you don't have a running program. Obviously, you have the linker as a program or a compiler as a program. They are all programs and processes running on the memory, but we are talking about the process of this source program. So until the load step, you don't have a process running in the memory. After you have loaded into the memory, then the process is an address is allocated for this process, and then we can say that a process is located in somewhere in the memory, and it has some base and limit registers, some base and limit values, and then there are some limitations about this process to where it can access or where it cannot access. And also we have some dynamic libraries, system libraries, okay? In Windows, for example, you can consider DLL, dynamic linkage libraries, or other libraries in the loading step. And finally, if you load this program into the memory, then we have some binary codes, some machine codes running in the memory in the operating system. So after this step, operating system is considering this as this program as a running process, and then after the allocation is completed, depending on the process state, as we already covered in the previous classes, it may be in the running stage. So there are some stages of the processes, some phases of the processes. So a process can be at a waiting status, or in a running status, or it can be in ready queue, or it can be in a terminated process. So there are some status, some stages, or some phases of the processes. So depending on the design of operating system, or the scheduler algorithm, or the behavior of the process, how it will, for example, it will request for accessing a file, let's say, and there is a lock on the file, so it will be on the waiting status. So depending on these conditions, we can decide on the status of the process. But basically, when you run a process, these are the basic steps of the process execution, and after you have executed a process, it is using some system resources which is allocated by the operating system. Okay, now let's talk about the logical and the physical addresses. So logical address is basically an address which is visible to the process. So process, for example, has a different address space than the real address spaces. So if we go back to this slide, for example, so the process is, let's assume, starting from 0 as the address space and going up in an incremental order. But in the physical address space, for example, this process can also be located in instead of this process, right? So we don't know which space is available, and operating system plays which space this process. So we say that process has a logical address which is visible to the process itself, and there is a physical address in the real world which is allocated by the operating system. So we don't know where this process will be placed in the memory by the operating system. So whenever we code a process, a program, we don't deal with the real world. We cannot consider what will be the scenario in the real world. So instead, we just deal with our own logical address spaces. So the logical address space is the address space visible to the process, basically, and the physical address space is the real address which is allocated for this process. So we have a relocation register. So basically, you are relocating some processes to the CPU, to the memory, okay? So you have a CPU here, and you have a logical address, and depending on where you have placed this process in the memory, you have a relocation register. So basically, you are reallocating this logical address to the physical address. Let's say this is the address you have placed this process, and it's starting from 14,000. Then basically you will add this offset value, this logical value, to the starting base address of this process. Okay, so that's how a physical address is calculated by using a logical address and the relocation register. Also, we need to talk about swapping. Swapping is an operation, basically replacing a process with another process. So swapping can be two ways. I mean, swap in or swap out. If you are swapping out a process from the memory, then you are simply moving a process to the disk, okay, a backing storage. Most of the time, the main memory and the backing storage can also be named as primary memory and the secondary memory. So in the secondary memory, we are talking about like some disks or SSDs, solid state disks, or some storage units, okay, which are relatively slower and relatively less expensive, let's say. In the main memory, which is relatively faster and more expensive, let's say, you have limited space. And this limited space is somehow should be managed by the operating system. And this during this management, sometimes you move processes out of this memory and you put them to the disk, or you can also put another new process into the memory. So that's the basic idea behind swapping. So you can swap in and out the processes. If a process is already ended, terminated, then this process will be removed from the memory, or a new process will be moved into the main memory from the disk. So we already covered the process control blocks. So whenever you move a process from the main memory, then you remove this process control block also. And also this swapping, later on we will talk about virtual memory. In this virtual memory we will say that we can use a part of back storage, secondary memory, as the primary memory. So whenever we are out of the user space in here, or whenever we want to optimize the main memory, we can use a part of the disk as a main memory. So we basically we back up some processes into the main memory, into the secondary memory, and then we can use them later on if we needed them. So this is the swapping in and out. So when you swap out a process from the memory, you simply remove it from the memory and put it into the disk. And when you swap in a process into the memory, then you are simply loading this process back from disk to the main memory. And the context switch, we already talked about this. Context switch is, as you can remember, it is the switching in the CPU. When you switch one process to another, we call it as context switch. And in swapping, we also have some time we spend for swapping in and out. So there is a cost for swapping in and out. And consider that main memory is much more faster than the secondary memory, so main memory should wait for the secondary memory to complete all the operations given by the operating system. So this is somehow a waste of time when you make an swap in and swap out operations. Okay. I'm gonna go for the limit registers we already talked. So in the relocation register, we start with the base value, base register, and then we add this value. So you basically check for the limit register if it is exceeding the process. But here we have something important. Okay, let's assume you have an operating system already stayed on the starting part of the main memory, and then you are allocating some spaces for the processes, okay? And let's assume this is the scenario. You have some processes already created, process 5, 8, and 2, and then let's assume you have ended process 8, somehow this process is ended, then you have some fragments in here, okay? And let's assume this is not the only memory you have limited, you have some other empty spaces following process 2, let's assume in a scenario. So you will have some empty space in here and some empty space just after process 2. So you have two gaps, two holes in the main memory, and we call them as hole. If there is an empty space between two processes, then this is called as hole in the operating system terminology. And this hole will, sometimes this hole is enough for putting another process, and sometimes this hole is not enough for holding any process. Let's say you have filled this gap, filled this hole with other processes, and then you have only a small amount of memory which is not available for putting any processes. Okay, so even in this case, for example, what happens if you terminate process 9? Then you will have a hole in here and another hole in here. So you see the number of holes are increasing and the size of holes are getting smaller and smaller each step. So this is a possibility in operating system, and this is a problem in operating systems. So we need a clever solution for this, and later on we will talk about paging and segmentation, and we will see how can we solve these fragments. We call them as fragments, and actually this fragment is called as external fragment. We will come them later on, but now you need to see that putting these processes continuously and using the best available place for this empty space is not efficient for the operating system, memory management part of the operating system. Okay, so one solution, one costly solution, not an efficient and feasible solution, is just moving all the processes and collecting all holes to one part. So for example, you simply move process 2, and if there is a hole in here, let's say you have terminated process 9, and you move process 10 here and then process 2 here, and then you can collect all the holes to the end of the memory, and you can have a bigger and larger space for allocating more processes. But this is a costly operation because you move all the processes. In the worst case, you move all the processes in the memory, so you basically get the process and copy the process, so it takes time in the main memory and it's not an efficient solution. So we need a much more clever solution. And here, where do you put, okay, you have, let's say you have multiple holes in here. Let's say you have a hole in here, which is the process 9 is already terminated. Let's assume it's terminated. There's a hole in here, and there's another hole in here. So you have multiple holes in the main memory, and you want to execute a new process, okay? And during this execution, you will select a hole for putting this new process. So which will be the algorithm? I mean, what will be the algorithm you want to use? There are some alternatives in here. So first fit is basically putting this process wherever it fits first. So you start from the start of the memory, okay, from the 0 address space, from the address number 0, you start and you go down like this, and if this hole is available, if the hole available here is suitable for this process, I mean the size is suitable, if the size is, the hole size is suitable for the process, if you can put this process in within this hole, then you can simply place it in here. Otherwise, if the size is not enough in here for the hole, for the process, then you jump over this hole and you try to put it into the next hole. So it goes on like this, okay? Search the main memory hole by hole, and the first hole available for this process will be the address that you are placing this process. In the best fit, instead of searching for the first available hole, you try to find the best fitting hole. So let's assume you have multiple holes again, and then you are checking for these holes and you are trying to understand which hole will leave the least fragment, least hole after you place this new process. So let's assume the size in here is just, let's say, 1 megabyte, and size in here is, let's say, 2 megabytes, and let's assume you want to place a 500 kilobyte process with these holes, okay? So you will search for this one, it is 1 megabyte, and after you place it, the half of this hole will be filled by the process, so you will only have 500 kilobytes empty space in here. And if in this case, if you place this hole, you will have 1 megabytes left after you placed. So basically, the smallest size, the hole size smaller after you place the process will be the selection criteria in this best fit. So you go for the smallest hole after you have placed the process. In the worst fit, just as an opposite approach to the best fit, you go for the highest amount of memory available after you have placed this process. So you search all the holes, you find the biggest hole you can place this process, and then you place this process and the largest into the largest hole at the end. So the approach in here is first fit is the simplest algorithm, so it is not complicated. You just go for the first place you can place this process. In the best fit, the idea is leaving the smallest possible hole after you have placed. So the approach in here is just using this hole in an efficient way. So in the best fit, you are assuming there will be no other processes placed into this hole. So if you, for example, place a process in this hole and you leave a very small space after the placement, then you assume that there will be no other processes placed in here. In the worst fit, you assume that there will be some space available after you have placed the process. So within this hole, there will be another process placed after the execution. So worst fit assumes there will be more processes placed into the same hole. Best fit assumes there will be no other processes placed into this leftover. Okay, what is external fragmentation and internal fragmentation? Okay, in order to understand the internal fragmentation, actually we need to talk about paging. But external fragmentation is the fragments between these processes. When you place these processes into the memory, there are some holes which cannot be used by other processes. So these are some wastes in the memory, and we call them as external fragmentation. In the internal fragmentation, we are mostly talking about the allocated space and the used space, because you know a process is not using the whole address space allocated for this process. So most of the time there are some unused spaces within this allocated, so we call it as internal fragment. Okay, and a solution is compaction or defragmentation. Sometimes we call it as defragmentation. Actually, defragmentation is a term for the disk most of the time, file system. But in memory, we also use this term, or compaction. So in the compaction approach, we basically move all the processes into one part of the memory and all the holes to the other part of the memory. So we try to collect all the holes in the same part of the memory. So we make a compaction. Okay, and let's start with the first approach for this problem. Okay, so compaction is costly. We already said that, so we don't like using compaction. Instead, we have some more clever solutions, a smarter solution. One is called as segmentation, the other one is called as paging. We will cover these topics, and also we will talk about using both of them together at the end. But let's start with segmentation. How do we do this segmentation in the memory? So first of all, a logical address, a program, has some units of memory usages. So for example, you have stack or symbol table or main program. Depending on your program, depending on your programming language, depending on your usage of the process. For example, a process may use some stack, or another process may use some heap, depending on the structure of the program. You place these related memory usages together in the memory. So for example, this is the process, this is a single process, and you divide this process into the subparts, submodules, and each module is placed into the consecutive memory spaces. Let's assume these are the basic modules of this process. You place the module 1 into the memory as a whole part. Okay, you don't divide 1 into 2 parts or 3 parts. You simply place 1 as a whole box into the memory. Okay, also 2 into some other place, 3 some other place, and 4 some other place. So operating system decides where to place these parts of the process depending on the empty spaces. So now we can talk about some optimization, because we can use these small amount of memories, some external fragments, for allocating some other processes. Okay, basically, if there is some small holes within these processes, and none of these holes are available, none of these holes are efficient enough for placing a process, you can divide this process into 2 parts, as shown in this figure, and you can use both of these holes in an efficient way. So this is the idea behind the segmentation, dividing a process and using these segments for this process. So operating system should keep a track of all the segments placed in the memory, because now if a process tries to access one part of these modules, then operating system should be able to point the exact address in the physical memory. So we again have a logical address in this scenario and a physical address. So conversion from logical address to the physical address is done by operating system, and it is very sensitive, very important in this issue. So let's assume 1, 2, 3, and 4 is the order of the modules, and in a regular approach we have them consecutively in the logical address. Now we divide them into the different physical addresses. So we need to convert, if this process is trying to access a part of this first segment, then we need to point to the physical address, the correct physical address in this case, as an operating system. Okay, so in the segmentation, we are talking about 2 registers. Each segment has its own base register and length register. So here you have a segment and for this segment we are keeping the track of the base register and the limit register. So you know the size of this segment, and you keep this as a limit register, and you know the starting point of this segment in the physical address, you keep it as a base register or reallocation register. Okay, here is the scenario for the segmentation. Let's assume you have the segmentation and you have placed several places of this physical memory, some segments, okay? And let's assume you want to access a logical address by using CPU, okay? The first thing you do is searching for the segment in the segment table. So you keep a segment table for keeping the track of all the segments in the main memory and their corresponding logical addresses. So you can convert easily from logical address to physical address by using this segment table. The only thing you do is getting the segment value, the segment number from the segment table, and then getting the limit and base values from the segment table. Okay? After you get the limit and base values, now you can check this offset value. So let's assume this limit is starting from 300 and base is, let's say, 300. So you can access from 300 to 600. And then there is an offset value, let's say 50 is the offset value, which means CPU, the process, is trying to access the given segment. Let's say this is the second segment, and this is the 50 offset value. So basically this logical address we are trying to access is in the second segment, and the offset value is 50. So we simply make a conversion from limit value and add this base value to the offset value, and we find the physical address. Later on I will make a numerical example, and then it will be much more clearer to understand how the segmentation is working. For now, just get an idea how it works. So there is a segment table, there is a segment number whenever a logical address requested by CPU, and this segment number is only used for converting the limit and base registers, base values in the segment table. And when you get this limit value for the given segment number, you simply make a check if it is a memory fault, an error, and then because you are trying to access some illegal addresses, let's say, if it is okay, if the limit is approved by the operating system, then you simply add this offset value to the base value, and then you find the physical address. And the paging. In the paging, we have a fixed size for the page, for the memory. So basically you have some page numbers, pages in here, and some frames in the physical memory. So you divide the physical memory into the frames. Let's say the page size is 1 megabyte, okay? Let's assume this is the scenario. So memory will be divided into the pages, and each page will be exactly 1 megabyte, and you divide the whole memory into the frames, okay? And we also have some pages, page tables. And when CPU is trying to access a logical address, then this time this page number is read from this request, and this page number is searched in the page table, and then the corresponding frame number is found, and we concatenate this frame number in front of this offset value, and we simply go to the paging value. Okay, one difference between segmentation and paging. In the segmentation we have some flexible, some unknown segment size, okay? In the segmentation we can use any size for the segment size, okay? We are flexible about using any size for the segment size. So we need to keep the base and limit values. In the paging, we simply keep the process into the pages. Let's say we have 10 pages for this process and 3 pages for another process, 7 pages for another process. So we will have multiple page tables. And in each page table, we will have the corresponding frame number for the given page number. So if you have 10 pages for this running process, for example, you will have some frame numbers for the corresponding page numbers. And then you make a conversion from page number to frame number, and you simply make a concatenation and adding a combining operation to the end of this frame number. Okay? In segmentation, you simply add, summation, the basic calculation as the summation to the base value, okay? So you make an addition in here. In the paging, you don't make an addition. You simply make a concatenation, okay? You combine the frame number and the page number instead of summing it with a base value. Okay, this is the paging. So let's go for an example. This is the logical memory of running process, let's say, and we have only 4 pages. And this is the page table, so we have 0 to 3, which are the page numbers, and we have the corresponding frame numbers. So, for example, let's assume what is the frame number of page 2? It is 3. So we can search this page 2 in the frame number 3. as you can see, physical memory is also divided into the pages, and the page size and the frame size in here. So we call these boxes as frame in the physical memory and pages as in the logical memory. Okay, pages in the logical memory and frame is in the physical memory. So this is a naming convention. But let's assume we have a page table which is converting these page numbers to the frame numbers. And then if you want to go for one of these pages, you simply jump to the corresponding frame number. And let's assume this is the 0, and let's say the page size is 100 kilobytes. And let's assume we want to access a logical address. Let's say the logical address we want to access is 150. Okay, so the first page will be 100, the second page will be another 100. So in the second page we have some addresses starting from 100 up to 200. So 150 is just in page 1. We can check this, and then we go to the page 1 in the page table, and we find that page 1 is placed in frame 4. So we go to the frame 4, and we know that this page, the whole page is placed in this frame. So 150 in here will be 50 because we have 50 as offset because it's starting from 100, and we can say that this is the 100th address of the first page. So we calculate the offset value in here, which is 50, and then we go to the frame number 4 and we check for 50 within this address. So let's assume it's starting from 0. Again, the page size applies for the frame size. So we have 0, 100, 200, 300, and within this frame, within this frame, we are starting from 400. So the exact address we want to access is 450. Okay, so the page number in here, let's say logical address 150, will be converted to 450 in the physical address. So you can make these basic conversions. Okay, so that's the scenario in here. For example, if you want to access F, then this is the page number 2. You go for the page number 2 and you find the page frame, corresponding frame as 1, and then you access this value, and then you can read the value over there. Okay, so this is the paging and segmentation. We will continue this later on in the next video, and then we will do some numerical examples on the following videos.